some iron looks like it shouldn't last. Rough surface, uneven texture, full of what we call flaws. By modern standards, it feels unreliable, unfinished. And yet, some of it has held under stress for hundreds of years. That alone is strange. Because when metal fails, it usually does so cleanly. A crack forms, then spreads, then everything gives way at once. Modern steel often follows that pattern. Strong until it suddenly is T. But old hand-forged iron, does T always behave like that? It bends longer, holds together, even when it looks compromised. Almost like the damage is being slowed down inside, which becomes even stranger when you look at its interior. It's not uniform, not smooth. Instead, there are lines, thin, stretched layers running through the metal, like fibers. Like the iron was folded and pulled apart over and over again. By today, S logic, that should make it weaker. But what if it does T? What if those irregular lines done T help cracks spread but interrupt them? Because a crack needs a clear path, and this kind of iron does T seem to offer one, which raises a quiet but uncomfortable thought. Maybe strength isn't T always about being perfect, and if that S true, then why do modern materials, so much cleaner, so much more controlled, fail so much more suddenly? Because resisting time is one thing, but resisting a crack after it begins, that S something else entirely. If you place a modern steel bar next to an old hand-forged iron one, everything tells you the newer material should behave better under stress, cleaner structure, controlled composition, fewer impurities. But the strange part only shows up when things begin to go wrong, because modern steel often holds perfectly until the exact moment it does T, and when it fails, it tends to do it cleanly, almost decisively, like the crack already knows where it wants to go, and nothing inside the material argues with it. It starts small, then runs fast, and suddenly the entire piece gives way with a kind of quiet efficiency that feels almost designed. But old wrought iron does T always follow that pattern, and that S where the contradiction begins, because in some cases R, even when the surface looks compromised, even when the metal has already taken damage, it keeps holding longer than expected, not by resisting stress completely, but by slowing down how that stress moves through it, which is strange, because inside that iron are all the things we retaught should make it: weaker layers, slag, fibrous lines, inconsistencies. And yet when a crack forms, it does to travel cleanly. It drifts, it hesitates. Sometimes it even splits into smaller paths instead of becoming one dominant break, almost like the structure itself refuses to agree on how to fail. And that shouldn't happen, because a crack is supposed to follow the easiest route, that S, the basic logic. But here the route isn't T clear, it S, interrupted, redirected, softened. And instead of one final fracture, you get a kind of internal fraying, subtle at first, almost invisible, where the damage spreads without organizing itself into a single ending. And that creates a tension that's hard to ignore, R, because modern engineering removes irregularity to eliminate weakness, while this older material seems to use irregularity to delay collapse, not stronger in the usual sense, but more forgiving. And those are not the same thing, because strength resists force, but forgiveness absorbs it. And in the real world, where stress is rarely clean or predictable, that difference starts to matter more than we expect, which leads to a question that feels a little uncomfortable. Because if this behavior wasn't fully understood, R, if blacksmiths weren't designing fracture resistance the way we do now, then why does it appear so consistently in the pieces that survived? Why does something so uneven behave in such a specific way? Because at some point it stops being just about the metal and starts to point towards something else entirely, the process that shaped it, and the hands that kept repeating it without ever needing to fully explain why it worked. We assume knowledge lives in books, in formulas, in precise instructions that can be repeated exactly the same way every time. But for most of history, it didn't work like that. It lived in hands, in movement, in small adjustments that were never written down. And a blacksmith didn't follow a fixed process so much as he followed the behavior of the metal itself. The color as it heated, the sound under the hammer, the way it resisted or yielded, and that changes what the final material becomes. Because when iron is worked slowly, folded, stretched, and reheated again and again, it does just take shape. It develops direction. Layers begin to align without ever becoming perfectly uniform. Impurities don't disappear. They get drawn out and distributed like thin threads running through the structure. Not clean, not controlled, but also not entirely random, which is strange. R, because no one at the time was analyzing internal structure the way we do now. No microscopes, no stress simulations. And yet, through repetition, through habit, through years of doing the same motions guided only by feel, something consistent began to appear, not in how the metal looked, but in how it behaved when it was pushed to its limit. And pieces made in different places by different hands sometimes share the same quiet characteristic. They don't fail all at once, and maybe that was intentional. Maybe no one ever said this out loud, but when your work depends on survival tools, hinges, chains, structures that have to endure unpredictable stress, you don't optimize for perfection. You optimize for something that can tolerate imperfection, something that can keep going even after it starts to degrade. And that kind of thinking does produce identical results. It produces variation, small differences in every piece, which modern systems try to eliminate. But here, those differences may have been part of the strength, because systems shaped by hand tend to accept irregularity instead of removing it. And in doing so, they become harder to break completely, not stronger in every moment, but less final when they fail. And that creates a quiet contrast with the way we build things now, because modern production depends on repetition, on removing variation, on ensuring that every piece behaves the same under the same conditions, which makes everything more predictable, more efficient, but also more uniform in how it breaks. Because when everything is the same, failure is the same too. And once the limit is reached, there is no disagreement inside the material, no hesitation, just a clean ending. And that S, where the older process starts to feel less primitive and more different, because it allowed the material to carry a kind of internal complexity that modern methods gradually removed, not because it was useless, but because it was difficult to control, difficult to scale, difficult to measure. And once you replace that with speed and precision, you don't just gain efficiency. You lose a certain kind of resilience, the kind that does prevent failure, but refuses to let it happen all at once, which leads to a question that feels harder to answer the more you think about it. Because if that resilience came not from design, but from the process itself, from repetition guided by human judgment rather than exact calculation, then what else was embedded in those materials that we no longer know how to recreate? Not because it's impossible, but because we stopped looking for it in the first place. At some point, without really noticing, the goal shifted, not from strength to weakness, but from endurance to precision. And those two ideas, always move in the same direction, because a perfectly controlled material behaves exactly the way it's designed to, right up until the moment it reaches its limit. And when it does, there's no hesitation, no internal disagreement. The structure gives way cleanly, almost instantly. And there's something efficient about that, something reassuring, because it means everything is predictable, everything can be calculated. But old iron does offer that kind of clarity. It bends, it strains, it begins to show signs of failure long before it actually breaks. And in that slow process, there's time for stress to spread out instead of concentrating in one place. Time for the structure to keep holding even as parts of it begin to weaken. Not perfect, not elegant, but not sudden either. And that difference comes with a cost. Because to create something like that, you need time, repetition, and a level of attention that can be fully automated. You lose speed, you lose uniformity, you lose the ability to produce identical results at scale. So naturally, we moved away from it. We chose materials that are easier to control, easier to reproduce, easier to predict, and for most purposes, that choice makes sense. Modern systems depend on it. But prediction has its limits, because real-world stress is rarely as clean as the models assume. It shifts, it accumulates, it finds the smallest certainty and pushes through it. And when everything is built to respond the same way, everything is also vulnerable in the same way. So when failure comes, it comes completely without warning, without transition. And that S, where the trade-off becomes harder to ignore, because what we gained in precision, we may have lost in tolerance. What we gained in efficiency, we may have lost in the ability to absorb the unexpected. Perfect systems break perfectly. And that leaves a question that, does quite resolve itself? Not about going back to older methods, but about what we stopped valuing along the way. Because Somewhere between the hammer and the machine, between variation and control, we didn't just change how metal is made. We changed how it fails. And maybe without fully realizing it, we also changed how we think about failure itself. Not as something that unfolds gradually, but as something that arrives all at once. And if that's true, then the real difference between old iron and modern steel isn't just in their structure, but in the way they carry the possibility of breaking. Because one resists the beginning of failure and the other resists its spread. And those are not the same thing, which makes you wonder, in a world built on precision, what happens when something finally goes wrong?